I don't know. They're just called Plymouths.
What does meter?
I'm sorry, I just had to start the recording
You
again.
should have got a ride.
Chicken. Does that chicken have a name, or is he going to be chicken food? Oh, shoot.
They don't have names.
Chickens
No,
are so
we
disgusting.
don't name
Oh
them.
my God, I hate chickens.
That's messed up, Ralph.
No, they can like they can all get extinct. Oh my! I mean, I'm saying this and I have Chick-fil-A, but still, like that's not the point. Oh wait, I said that on while you're recording. Oh my God! Oh my God! Now the internet's gonna go. Oh my God! The left wing
I feel like
protesters.
this
This and that.
is an important way to start our laboratory exercise.
I think so. I thought this would be a great contribution. You know, everybody's got their dogs, and this is what I got.
What would the world be like if there weren't any birds? What would the world be like though?
Yeah.
There would be a whole lot more
It'd be
bugs.
pretty lame, dude. I really like chicken.
Oh,
Jesus.
Yeah, that just made me. Ugh, no. I have to cook chicken all the time at work.
You can cook mine.
Oh, speaking of which, I have work in an hour.
Yeah, we
Well,
should
that's
get
fun.
going soon. Let's resume the recording. And with that brief interlude to check out Nathan's chicken, we are now back and we are ready to do the period-luminosity relationship, which is lab number 12. I have in my hands the period-luminosity relationship laboratory exercise, which is available on Blackboard. You can download that. I've got some pencils and a ruler, and of course our trusty Casio calculator. Now, the work that we have to do today is relatively minimal. It boils down to about making 2 graphs and doing a quick analysis section. But in order for you to get the full richness of this exercise and understand why it's cool, Greg, the page number in your lab book is 16. So you need all the pages, well, most of the pages from 16. We're going to start at page 16.3, but we're going to be using many of the others as well. So let's begin by starting at page 16. We actually have to have a talk about variable stars. So let me go to my share screen for a moment here. And let's do a little discussion about Cepheid variable stars. If you could look at a variable star, if you could fly up to it and sort of check it out from the perspective of a spaceship, this is sort of what it would look like if you could stand astride a variable star. Variable stars pulsate. Their radii grow and shrink with time, and a typical pulsation period for a variable star might be like a month or 30 days. But there are different types of variable stars. Some have long periods of pulsation of several months. Some have short periods of pulsations of 15 days. And it turns out that there's a relationship between the mass of or the size of a star or the luminosity of a star and how quickly it pulsates. And one of the first people to discover this was one of those Harvard computers that we learned about in chapter 15. You guys will remember that in our lecture on the history of the spectral types of stars, there was this legendary astronomer, Ed Pickering, and he had a number of
That's legendary.
a number of computers that helped him analyze the spectra of stars. One of these, by the way, you'll remember that you could actually see them observing a Cepheid variable star in this famous photograph. Over here against the wall, they're looking at a variable star named Beta Auriga in 1889, and you can see they're plotting its magnitude as a function of time, watching it get brighter and dimmer in our sky. One of these ladies who was the first person to discover the variable stars is now an astronomer of great legend, and her name was Henrietta Swan Leavitt. I think I have a picture of her in one of my later slideshows. Hold on a second, guys. Let me see. Okay, hold on. I have so many slideshows open. that it's getting a little difficult to find the one I want. So just bear with me here. Stellar evolution, relativity, stellar death, the Milky Way, or galaxies. I believe it's in galaxies where I have a couple of plots of this. Okay, so the name of this astronomer who first discovered variable stars was Henrietta Swan Leavitt. And there's a, of course, a Wikipedia page about her contributions. Her claim to fame, Henrietta Swan Leavitt, is she was one of the Harvard computers, or one of Pickering's harem there, who was responsible for discovery of variable stars. But not only did she discover the variable stars, she figured out how to do some cool physics in astronomy by analyzing their period of pulsation. So basically, the lab that you're doing today is you are walking through the seminal research that she did and trying to understand why it was so important. So allow me to go back to this slideshow here. And I want you guys to imagine finding a variable star in some distant place. Okay, so we look out into the galaxy and we find a variable star like Polaris or Beta or Riga, and we measure its period of pulsation. Now, remember, these stars are literally just pinpoints on the sky. They look like little stars, and we watch them over the course of a month, going from dimmer to brighter to dimmer again. And just like you could see in that graph, they're plotting the brightness as a function of time. You're actually going to be doing this in your lab today. We can then measure the period of pulsation by measuring the time from this peak to this peak. Sorry, my drawing isn't very good. And this distance here gives you the period of the pulsation. Henrietta Swan Leavitt compared the period of pulsation to their magnitude, or their absolute magnitude, or their brightness, and she discovered a legendary graph that looks like this. It's called the Period-Luminosity Relationship. So what we're plotting here is we're plotting the period on the x-axis, and we're plotting the absolute magnitude, or the luminosity, on the y-axis. And I want to explain to you why this isn't so important. The luminosity is a property of a star that we would like to know, but it's not very easy to know. And that's because the luminosity of a star measures its total light output in all directions. Literally, the only way to directly measure the luminosity of a star would be to somehow fly to that star, to cover that star in some kind of a giant solar paneled sphere, like a Dyson sphere, and then measure all of the photons that it releases, which of course is impossible. We don't have the technology to do that. So we have to find their luminosities through trickery. However, after discovering their luminosities through trickery, Henrietta Swan Leavitt made a graph of the period versus the luminosity of about 50 to 100 variable stars. And this graph became a tool that we could use to measure the distances to stars. Remember, of course, from our earlier lectures, that we can always measure the brightness of a star. So let me go to chapter 15 here. Oops. Just bear with me here. I'm trying to make an argument, and it's taking a little bit of time. Oh, shoot. Did I just close that slideshow? I think I did. Okay. At the beginning of chapter 15, I reminded you about the inverse square law and the fact that we can rearrange the inverse square law to compute something called the luminosity distance. The luminosity distance tells me that if I measure the brightness of a star with my CCD camera, and if I also know its luminosity, I can compute the distance to a star. The annoying part is getting the luminosity. That's not something that's easy to do. But Henrietta Swan Leavitt made it easy to do if you could find a variable star nearby. '43. The idea is that once you have Henrietta Swan Leavitt's period luminosity relationship, You can find a variable star with a period of 10 days. You can use her graph to go up to a star with a period of 10 days and then go over, and that allows you to measure the luminosity of a star or infer the luminosity of a star because there is a tight correlation between the period-luminosity relationship. Now, this played an important role in the history of astronomy because Edwin Hubble used this graph to measure the distance to the Andromeda Galaxy. Back in the early days of astronomy, when people would see these little swirls of light and gas, they didn't know if they were looking at just cool nebulae in our own Milky Way galaxy, or if these things constituted other galaxies, or what Immanuel Kant called island universes. Hubble was able to find a Cepheid variable and resolve it in the outer arms of the Andromeda Galaxy. And he was able to measure its period of pulsation. He then used Henrietta Swan Leavitt's period-luminosity relationship to figure out that the distance between this galaxy and our own Milky Way was 3 million light years. And that proved that the Andromeda Galaxy was not just a little nebula inside the Milky Way, but was an island universe. Today, you will attempt to do the same thing. Let me walk you through the two graphs that you're going to be making for me today. First, you're going to measure the periods of a bunch of Cepheids, and you're going to construct Henrietta Swan Leavitt's period-luminosity relationship. Then, I am going to give you the period of a pulsation of a variable star in a nearby galaxy. You will measure its period, you will compare it to its luminosity, and you will use the inverse square law to get the distance to the galaxy. Are we ready to go?
Yeah.
Okay, so that sounds good to me too. Let me exit out of here. That was the preamble. And now what I want to do is I want to go to share phone mode, and I want to give you a couple of extra details. Just a sec, guys. Share screen, iPhone, Zoom, and camera. Okay. Here's the first thing that I need to teach you guys. There's a slight difference between the simple graph that I showed you earlier and the real period-luminosity relationship. First of all, Henrietta Swan Leavitt did not actually plot the luminosity of a star. She plotted capital M, the absolute magnitude. Do you guys remember what that is? Because if you don't, this is going to be a sort of confusing lab here today. What is the meaning of absolute magnitude? What's its definition?
Is that its brightness not based on its location?
Yes, more or less. It's the apparent magnitude a star would have if it were fixed at 10 parsecs. Fine. That's good enough for me, Michael. Thank you very much. Also,
You're welcome.
I told you that she plotted the period of the variable star, but it turns out that it's not linear if you plot it by the period. You have to plot the log of the period. Do you guys remember what the hell log is from your math class? We need to have that discussion before we go forward today. What does this function do? Anyone? Nobody knows what a log is?
I don't know. When I pressed 1 and then hit log on my calculator, it made it 0.
Yeah, I'll tell you why. Log is designed to answer the question 10 to the power of x equals something, like 100. Let's see if you guys understand this. Do you guys know what the answer to x is there?
2.
That would be a 10.
No,
No, 2.
No.
2. Because
2.
10 squared is 100, right?
Yes.
Okay, what if I did this? 10 to the x equals 1,000. What's x then?
3.
Exactly. What's x now?
on my game today. 4.
What if it's 100,000?
5.
What if it's 10 to the x equals 54321?
Well, I got all the previous ones, so I think someone else got it.
It's 4.73 and more.
Oh, Morgan knows what to do. Right. Morgan, you know that. So this is 10 to the 4 and this is 10 to the 5, right?
Yeah.
And this is somewhere in between 10,000 and 100,000. What you do is you invent a computer program which will raise 10 to every power between 4 and 5. 10 to the power of 4.01, 10 to the power of 4.02, and you tabulate a log. The purpose of log is to solve for x. So what we do is we do log of 54321, and that solves for x. Now Morgan already kind of knew what to do, so why don't we try it together? Okay, so let's see what Morgan did. Take your Casio calculator, do 54321, okay? And then hit log. So Morgan, you already knew how to do that, didn't you?
Yeah.
Okay, cool. Okay, let's try to start with the first page of our lab. Bear with me, guys. I'm going as fast as I can, all right? Here in the first page of our lab, which is 16.3, we see a number of variable stars in a star cluster named, what is that? Is that Zeta Persei? I can't remember what this, or is that Zeta? I have a little book that tells me what all these symbols are. Okay, they've given us the period, the log of the period, the apparent magnitude, and the absolute magnitude. Now, to calculate the absolute magnitude, we have to use the following formula, which is in the lab, but I think I can remember it from heart. It's the oh shucks. The absolute magnitude is the.
Oh, that's chi.
Oh, why is that cheating?
No, that's the symbol's chi.
Oh, is it chi? Thank you. Thank you for looking that up. So
Yep.
chi. Or kai. No, I'm sorry, it's kai. It's pronounced kai.
Yeah, it's CHI. I didn't know.
Yeah.
I was
In
just doing
Greek,
my best, man.
there were no soft C's in Greek or in Roman. So it's not even Caesar, it's Kaiser. So it's Chi. Okay. The absolute magnitude of my star is the apparent magnitude plus 5 minus 5 times the log of the distance to the star cluster. And the distance to this first star cluster, Chi Persei, is 2,600 parsecs. So the distance to this star cluster is 2,600 parsecs. And are you guys writing all this down?
Yes.
Thank you.
I don't think I know you do. They tell me you messaged them.
I don't know if they're writing it down though.
Yeah.
Hold on, I can't see that equation.
I was talking to Missy Lee.
See?
Oh, that's because my phone pooped. Hold
We
on.
had a really good week last week, and this week is even better.
Hold on. We got to do that thing again. I got to go to my settings. Display.
She's also liking the fact that you get your 10 activities done. She says, then you can play all the video games you want.
Okay. Whose background is that? We want to, it's not that I don't love to hear your mom shouting at your brother or whatever, but it's not helpful for our class here. So let's go to, I've got to.
Sorry, that's me. I still lost the equation.
Oh, okay. Wait, is that with the background noise?
Yeah.
Okay, sure. Just mute yourself after you comment, right? Riker, don't stop contributing and I will get you the equation, but just mute yourself so that we don't hear all that. iPhone, share screen. Just a moment, Riker, it's coming. All right. Can you guys see that okay?
All right, I got it now.
All right. So guys, we have the apparent magnitude right here, right? So we're going to have to do these computations, 8.36. So the first one is going to be 8.36 plus 5 minus 5 times the log of, actually, hold on. I need a bigger piece of paper to write this out on. This is the first time I've ever, oh, whoa, there's a weird lag. Sorry, guys, I'm seeing what I did like 5 minutes ago happen on the phone. Okay. So our first apparent magnitude is 8.36. So the absolute magnitude then is going to be 8.36 plus 5 minus 5 times the log of 2600. Can you guys see that?
Yeah.
There's a really strong latency, a really strong delay. Okay, let me tell you how we're going to do this. We're going to punch this plus this minus that that. We're going to hit 2600 and then log, and then we're going to hit equals. Okay.
All right.
So watch me do that now.
Oh yeah, there's a huge delay because you're just putting the arrows down now.
Yeah. Hold on. Let me stop sharing because that delay. It's normally not that bad. That was messing me up. When I talk, I can see myself talking, but that was some crazy delay. Okay, that's better. All right, let's try this. We're going to do 8.36, right? Plus 5 minus 5 times 2600 log equals. You guys get that?
Yep.
Negative 3.71 is what we're going to keep. All right, can you guys do the rest for me?
Is the distance
Yep.
the same?
So next is 7.99, right?
So that distance is a constant.
Yeah, because all the stars in Chi Persei are in a cluster, so they're roughly the same.
Okay.
So we'll do 7.99 plus 5 minus 5 times 2600 log equals negative 4.08. Okay. 7.56 plus 5 minus 5 times 2600 log equals negative 4.51. $719 plus 5 minus 5 times 2600 log equals negative 4.88. Okay, now our goal, ooh, I've got some highlighters here. Look, a jar of highlighters. Our goal is to plot log P versus apparent magnitude. But not only are we going to use the stuff from Chi Persei, we're also going to plot other Cepheids onto the same list to make a period luminosity relationship. So we got to plot these, and we got to plot all of these on the same graph. You guys ready to do that?
Sure.
All right.
Yep.
let's turn the page to, I don't know, the page number, shit, isn't on mine.
It'd be like 16-5.
Yeah, it looks like this. It says figure 1, period luminosity relationship. Okay, we're gonna have to be smart about this here. Our first data point is 0.73 versus negative 3.71. So where would 0.73 be here? This is 0.7, right? What is each little tick mark worth here?
2.
Ross,
Or
what is each tick mark worth?
0.02.
0.02.
Yeah, it's 0.02 per tick, right?
So going between 2 ticks away and 1 tick away.
So there's
Right
my
there.
memory tick. It's right about there, right? Okay.
Yep.
And then this is negative 3.71. Watch out because negatives go upwards here. That's minus 3.5. What is each tick worth here?
0.1.
0.1.
0.01.
0.1, yeah.
So
Oh, is it
that's
0.1?
negative
Yeah,
No,
3.6, negative 3.71 is right there. So let's find the intersection of those two. Oh, it would help, honestly, if I took off screen lock. I have to hold it if I do this here. But, 2.7, all right. I need both hands to do this, so. Okay. I'm gonna go up. The ruler is gonna be at 0.71. I'm gonna have to streamline this process a little bit. That's my first data point. Did you guys
Yeah,
get
I
that?
use a stick and another stick.
Yeah, a couple of rulers can help. All right, let's keep going. Let's get the next one. 0.74 and 4.08. So there's 0.74. I think I like this other ruler better. It's negative 4.08. It's very easy to make a mistake here, guys. 4.08, that's negative 4.1, so negative 4.08 is just below 4.01, all right? So I'll go across here. Okay. So work with me, keep going. 1.04, negative 4.51. 1.02, and that's 1.04. Negative 4.51, this is negative 4.5. It's basically at negative 4.5, more or less.
Yeah. Oh, shit. Where'd I put it? Oh, there it is.
During the course of this lab, I normally patrol and watch and make sure students are doing it right. This is a little dangerous because I can't see what the hell you guys are doing. So basically make sure your shit starts to look like my shit, for lack of a better way to put this.
Descriptor.
Yeah. Positive 1.13, negative 4.88.
Oh, I
This
just
is
plotted it.
1.1. 1.12, 1.13 is right there. Okay. And then 4.88 is close to 4.9. So I'm going to go across at 4.9.
Gesundheit.
Thank you.
So those are my first four. Is that what it looks like on your paper, guys? You're going to have to turn this in, by the way.
No.
Yeah, that's about what it looks like on mine.
Okay, that means we've done the plots for Chi Persei. Now we got to go to
I
other.
don't.
Hold on.
Oh, I think I messed up somewhere.
How can I help?
I thought I was keeping up, but I only have 2 points.
Riker,
so
you ready to take
I
a photo?
slipped up somewhere.
Did somebody,
Wait,
do you need me to take a
hold on.
screenshot?
Wait a sec. I'm trying to get my, there we go. Sorry, Riker, try this again.
Did we want me to take a screenshot of that?
Yeah.
If
This
you
is
could, that'd be lovely.
All right. Do you, you're part of the Discord, right?
Yep, I am. Thank
Oh,
you.
wait. Riker, let me stabilize it.
I've already taken
Ow.
a picture of
All right, okay, fine.
it.
Guys, we're not done. We got to plot these now, right?
Yeah.
All right. So we got 0.49 and negative 2.9. So this is 0.48. That's 0.49. Negative 2.90 is basically right here, just below 3.
Oh, come on. Damn it.
What's wrong?
It's not letting me send that picture through the Discord.
Why not?
Can you put it in the chat?
Yeah, you can send it to the chat, I think.
Can I?
Yeah, because I can look at that just as easily. Actually, probably more easily.
I'm
for
moving
me.
on to 0.71 and negative 3.84. Keep up with me. Here's 0.71 and negative 3.84 is halfway between 3.8 and 3.9. I think I did that right.
Yeah.
0.65 and negative 3.78. So 0.65 is here, and negative 3.78. 3.78 is almost negative 3.8. Okay, oops. .83 and negative 3.63. 0.83 is here, and negative 3.63 is right about there. That's negative 3.6 right there. Okay. 0.9 and negative 3.62. So 0.9 is right there. Negative 3.62. Negative 3.6 is right there. Just above negative 3.6. Oh, weird. Do those have the same? Oh yeah, negative 3.
About. Just about.
Yeah.
That's
Okay.
by 0.01.
You understood what I was saying. You think that was cool, Riker. I'm glad that you understood me. 0.99 and negative 4.27. So here's 0.99 right before 1, halfway between, and then negative 4.27. Negative 4.27 is getting close to negative 4.3. So I'll put my line at negative 4.3. And that was 0.99. So we got one more to go. 1.62, negative 6.25. 1.62 is right there. And negative 6.25, that's negative 6.3. So negative 6.25 is halfway in between. I'm going to put my ruler at negative 6.3. I'm going to scan over to 1.6. And I'm going to go up. Bam. Hold on. Riker, you want to snapshot that for everyone? Hold on. Wait a sec, Riker. Riker, will you snapshot that for everyone? Let me know when you got it. Riker?
Riker, I don't think your mic's working.
Or his family is talking,
Riker?
so he's waiting. He got it. Yep, I was right.
Oh, he got it?
Yep.
All right.
Yep,
Okay.
you said I got it.
All right.
My mic came slightly unplugged.
That's okay.
Ah,
All right. How are you guys doing? Do you have this? Or can we go forward, or do you need a second?
Still plotting.
Yeah, you guys might be plotting
Yeah.
a little slower than me, so let's give you all a sec.
About halfway done.
I'll take a sip of iced tea meanwhile. I enjoy some iced tea. This is our period luminosity relationship. Nathan, was that chicken for eggs, for meat, or for pet?
We sell eggs. So yeah, eggs.
Can you taste the difference between fresh eggs like that and the ones at the
Yeah.
store?
Definitely. That's
Must be
yeah.
totally amazing, huh?
I mean, because of the fact that we have so many eggs, I don't really like eggs anymore, but it is a lot better.
They're like a perfect food. They're like a perfect food.
They are.
All right. So
We have a
whoever's in
never-ending resource, so.
the Discord, it's in the lab pictures.
All right.
thank you.
Look, we've got another task to do right now. Let me flip this thing. Our next task is we have to draw a best fit line. And I want you guys to watch me do this. Now, the best fit line is the line that minimizes the discrepancy between the lines and the points. And basically on our graph, it's going to kind of work out that if you get this guy and you get this guy in the graph, if you connect this point and this point, that's going to be pretty damn close to our best fit line. It's not always quite so simple, but that will minimize the deviations. Now, I'm going to put this back here. Unfortunately, I don't have a tape holder that can hold. I haven't figured out how to hold my phone. Oh, maybe like. Oh, wow. Here we go. I'm a damned genius. Okay, so check that out. So I don't know if you guys can see what I just did there, but I'm kind of proud of myself. I used this little optical holder for my phone.
Oh, yeah.
Okay, so here we go. I'm going to sort of make my best fit line. I'm going to hit the top point up here and the bottom point there. And I'm going to go all the way across the graph, all right?
The only thing I have long enough is a meter stick, so.
You can also use the edge of a notebook, or yeah, if you have a meter stick for some reason, that's cool. That's what the best fit line should.
I mean, it's a yardstick, but I didn't want you to be disappointed.
By the way, don't get confused. This is not a point. Ignore that crap down there.
I'm just using my history textbook.
That's a good use of history.
Riker, you want to snapshot that too, just for the hay of it?
Riker, that's rough, buddy. I'm trying to be a history guy.
Oh, you do it with your phone? I thought you did it with a screenshot.
I did do it with the screenshot, but the problem is that when I screenshot it, it's too big.
Oh, the file is too big?
Yeah,
Huh, okay.
I know
That
it's
makes
weird.
sense.
All right. We
Okay,
have our period luminosity relationship, and now we can put that graph on ice for just a moment. Now we've got to go on to our next business. We're going to go to the Large Magellanic Cloud, and they've given us the data for the period versus the apparent magnitude of a Cepheid variable in a Large Magellanic Cloud. If you enjoyed that last graph, well, you're going to love this next one, because we're going to be doing yet another plot. Hold on a second here. This time on page, oh, it's on the back side of that. It's figure 2, the light curve of a Large Magellanic Cepheid. So basically what I need the class to do, and what I'm going to be doing here with you, I'm going to do it too, is we're going to plot time versus magnitude on this graph, okay? Hold on, guys. I need to get an optical holder here. This thing doesn't tip over. This is what I need. Oh, wait. Huh. Nope, that won't work. Okay. All right, never mind. Bad idea. Sorry, guys. I thought I was smart, but then I discovered the truth. All right. Let's get to it.
I mean, that's tragic.
So our first point, this is going to take a while, 1.28, 1583. So here's 1.5, 1.28. Let's just round it. Let's just call this 1.3. That'll make this a little bit easier. And we'll call that, I don't know, 15.8. So here's 1.3 right there, right? And then 15.83, 81, 82, 83 is somewhere around there. We're just going to round it off just to make it a little easier to manage. So 15.83 and 1.3 is right there. Can you guys see the trick that I just played there? Let's get back. Let's get vertical again.
Yes.
That trick will probably help us. Okay. We got that one. You might want to check them as you go. 1.4 and 15.95. So here's 1.4 and 15. Watch out, the numbers go upside down. 15.9 is here. So 15.95. Sorry. 9, sorry. Wow, I did this badly. This is 15.7. So when I was trying to do 15.83, that's 15.82. 15.83 was there. Did you guys see that I made a small mistake?
Yeah, I was gonna correct you.
Thank you, Morgan. Thank you, Morgan. Let's watch out for that. Each of these ticks is 0.02 per tick, right? Okay. 1.37 or 1.4 and 15.95. So there's 1.4. And this is 15.92, 94, 15.95 is right there, all right? .6 and 15.6. 1.6 and 15.6. Ooh. 15.6.
Yeah, that one was easy. I was like, oh, thank you, God.
Okay, keep going. 1.84, 1.8 and 15.26. So 1.84 is 1.8, and then 15.26, whoa, 15.3, 15.2224, that's 15.26. I need a ruler for this. 15.26 is there, and 1.8 is there. Go all the way up. Boop. Make your data points easy to see. Whew, that thing's going up. 2.2 and 15.2. 2.2
Oh shit.
and 15.2.
Motherfucker.
I feel that, Jonathan.
Yep,
That wasn't me.
that was Riker.
That was me.
Wow. I feel that, Riker.
I'm looking at the wrong friggin' spots.
I know. This is tough, guys. 2.3. Remember, we're rounding the time column to the nearest tenth to make things easier.
It's the 15. The fact that it's going backwards is screwing with me.
Yeah, that's what keeps getting me.
Watch that, guys. It goes smaller upwards, right?
Yeah, that's definitely screwing with me.
15.23.
Why would they do this?
To torture us.
2.3.
Have I not suffered enough?
15.23 is 15.22. That's 15.23 right in the middle.
What was that? 2.3 and 15.3?
15.23. So remember, this is 15.2.
Oh.
That's 15.22. And that's 15.23 right there, halfway in between.
216 is 15.2.
Oh.
Right?
My sentiments exactly.
So this is
Yep.
2.7 and 15. 2.7 and 15.32. 2.7 and 15.32 is right there. .2 and 15.41. 3.2 and 15.41. This is 15.4. And if we go down, that's 15.42. 15.41 is right in the middle. All right. This is just going to be 4.0. Make that 4.0. And this is 15.51. So there's 4.0. And 15.5 is here. sorry, that's 15.50, right?
15.51.
Is right here. That's 15.51. So I'll go across at 15.50 and I'll find 4.0 and I'll just go right underneath it. That's my trick. Okay. We're getting through it. This is 4.2 and that's 15.56. So 4.2 is there. And this is
That's
15
4.1.
No. Oh, fuck. Yes. Duh.
Yeah, we all suffer here. We all
That's
suffer here.
been our sentiments this whole freaking time.
Thank you.
Now realize.
4.2, right? Thanks for catching that, man. Hey, it takes a village to make a graph, okay? So 4.2 and then 15.56. This is 15.5254. That's 15.56 right there. Okay. 4.2 again.
There's still so much left.
15.63. Come on, we can do this.
Yep.
4.2 and 15.63. So 4.2 and 15.63.
Nice.
This is 6.2. That's 6.3 right there.
All right.
We're at the halfway mark now.
Yep.
Ha!
4.5,
Mark, because-
15.7. So here's 15.7. Okay. And then we go to 4.5 and we go up. Boom.
Yeah, this one's pretty easy.
Yep.
Yeah, that 5.2 one is nice.
5.2 and 15.84. 5.2.
That's not bad either.
You
15.
you appreciate the little things.
Yep. 15.84 is here. Well, if we were a little more modern, we'd be doing this in Excel. Wait, was that, sorry, that was 5.20. Whoa.
Yep.
Wait, so which one are we rounding? The 15?
We're rounding the time category only to the nearest tenth. So 5.2 was already rounded for us, but this one would be 5.4. We are not rounding this one.
For a while.
Say that?
That also confused me for a while, but I got it.
It
Yeah.
makes sense though, right? 'Cause it's hard to split. It's hard to split this into 10, but it's easy to split this into 2. I was going to explain it, but then it was going to be more words, more time. You know what I mean?
Yeah, no, I get it. I was just double checking. Thank you.
So I did this one. Now I'm going to 5.4 and 15.84. So this is 15.84 right there. And that's at 5.4. Okay.
That's pretty good too, Riker.
5.9 and 15.85. This is 15.85 right here. And that's 5.9. I think I did that right. Okay. This is 6.0 basically, and 15.93. So 15.93 is right after 15.92. And that was 6.0. Okay.
Oh, this is a new form of evil.
Yeah. If we were more
really
modern,
glad I had the lab book.
we'd plot this out in
Holy
Excel, but we're doing it old school style. So 6.3 and 15.61. So what we're going up again, so watch out for that. 15.61 is just below 15.6, right? So this is 15.6. It's going to be at 15.61, and 6.3 is here. There we go. Okay. 6.5 and 15.3. 15.3 is way the hell up here. And 6.5 is right here. That was easy. Okay.
Who is that?
Sorry? $6.9 and 15.19. So 15.19. Wow. This is 15.2. So 15.18 is here. 15.19 is right in between it. And that was 6.9. So almost at 7.
Never mind, yeah.
Right there. 7.5 and 15.33. So here's 15.3, 15.32. That's, oops. That's 15.33 right there. And 7.5. Okay. Almost done. 7.9 and 15.39. So 15.38 is here. 15.39 is just above 15.4. And that's 7.9. Whew. 8.7 and 15.5. Okay. 8.7 and 15.53. 15.53 is right there. I don't know how you guys are doing with this, but I'm getting there. 8.8 and 15.56. So 15.52, 15.54, 15.56. And that's 8.8. 8.8, 8.8. I think that's right. 8.9 and 15.64. 15.64 is here. And that was at 8.9. sorry, 15.64 is here. And that's at 8.9. No. Wow. I almost made a mistake there.
Yep. I feel that. That was me last one.
And one last
This one's
one.
an easy one.
9.2 and 15.7. Am I going slower than you guys? There's 15.7.
Nope.
There's.
Please tell me this is the last chart.
Yep.
It is.
We got more to do though. Okay. Holy God damn it. Did we have a thing to do there?
It was so far away. It was
That's
so
what I
far
got.
away.
Riker, snapshot that. Someone snapshot that.
All right. Riker, I believe in you.
Trying to hold it steady.
Hope, I like the other mug more. Yeah, that one's great.
What are you talking about?
Nothing. Just hanging out.
Tease and hope. Okay.
No, I would never.
Guys, we have to make, it's not a best fit line this time. It's a smooth organic curve. Now look, only Pee Wee Herman connects the dots, la 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 la. We have to make a smooth organic curve, okay? So watch me try to do this. It's gonna come up like a sawtooth, right?
Mm-hmm.
So,
Oh, we're basically connecting these.
well, it's not
No,
connected.
only Pee Wee Herman connects the lines.
Yeah, you have to go kind of like in between them. Do you see how I'm doing this?
Yeah. Well,
Like an average.
Yeah, like a best, they call it a best fit curve instead of a best fit line. Sorry, this got a little messed up down here.
Does it start at the corner? Or
This is what
the
mine
first?
looks
Okay, it starts at the first dot.
like. Do you see how it has a sawtooth wave? That is, they call this in signal processing, they call this a sawtooth wave. And this is a total classic thing. Variable stars don't have a perfect sinusoidal oscillation. They obey a sort of sawtooth where they rise rapidly and then they have a linear fall off. They call this a sawtooth wave. If you're into synthesizers like I am, sound waves that look like this produce some kind of evil synthy sounds that sound really cool. They sound like cool, just evil synth patches. They're great. All right, are you guys at this place here right now?
Yeah.
yep.
Yep.
Getting there.
Does anyone need a moment? You need a moment, John?
Yeah.
Got it.
That's
I
okay.
just
If
need
you
to
a
check my
moment, other
pulse real
people
quick.
probably do too.
Yeah, I'm good.
John, let us know when you're good, okay? We're just going to kind of
Mhm.
keep it here for a moment. So you guys see what our first objective is, right? What are we going to need to do here? What's the single most important
we have
property
to-
of a variable star? What do we want to get?
Plug
from it?
everything in the top right.
All right, what does the first thing ask for in the top right?
Big P.
What does big P stand for? What does that mean, big P?
I don't want to know.
Is that period?
The period. Michael, how do you think we should get the period of this variable star?
Well, if we look at the days at the bottom, right?
Okay, but where do we start and where do we end?
Can we start at the top of one of the curves and then stop at the bottom?
Excellent idea. All right, watch me do that. Jonathan, is it okay if I start moving forward?
As long as it's nothing too complicated.
All right, let's just give Jonathan one. Well, we're just going to do this one thing, and then we'll give Jonathan this. I'll do it really slowly.
Okay.
I'm going to make a vertical line. Do not use the points. Use the curve. So I'm going to do mine, I don't know. Do I want to bias it towards 2? Let's keep it simple, I guess. Yeah. Or do I? Let's make it 2.1. Oops. That's my first peak at 2.1. Let's get our second peak. Don't use the exact data point. Use like the top of the peak, which I think is, I guess it's close to 6.9. John, where are you at?
I'm almost done plotting.
We could have done 7 and 2, and it just said 5.
Well, I don't think it's, but
instead
I'm
we
not
want
a
to go with a
numerologist.
4.
I'm trying to get the real period, not what I want the period to be, right?
4.8.
So what is each tick mark worth again? 0.1 days, right? So it's
Yeah, so it's 4.8.
4.8 days. Everyone buying that?
We're on like week 2 or 3 of quarantine. I don't have any money.
Two. Month 2.
Okay.
Dude, I don't know how time works.
John, where are
anymore.
you at? I'm trying not to leave you in
I've
the
also
dark.
been working, so I'm just a liar.
Hold on, Michael, can it for a second. Well, John, where are you at?
Almost. I'm on the last point.
Forget about the last point. Just draw your best fit curve and get your period like we are doing. Okay. Class, up here for our period, 4.8. That's days, right?
Yep.
How are we going to get log P?
Do we put in 4.8 and then hit the log button?
That's exactly right.
Oh my god, man. This stuff is easy.
You
I
should
got
ask a
0.68.
physicist.
0.68.
Yep, let's write that down, 0.68. Okay. Now, remember how we had a period luminosity relationship before? That's how we're going to get our big M. So, go to the other side. Let's find 0.68, which is just before 0.7. Got that? Take your ruler, go up to the line, not to the data points, but to the line. Once you get to the line, then we go over.
Negative 3.45.
I got negative 3.5. Mine's a little closer to 3.5 than negative 3.45, but I could see how that might have happened. If you look at where my intersection is, my intersection is there. Sal, let me zoom in here.
I'm at about 3.45 myself.
Your
Oh,
line's
really?
Yeah, our lines are a little different, but
Right. You can see my line was a little closer to there, but if you had drawn this,
No, mine's at like 3.4.
it should work either way. I'm going to go with mine is negative 3.5, but negative 3.45, as you'll discover, will work just as easy.
I'll put 3.5 anyways.
Yeah, I guess so. I mean, I'm not saying, Sal, that my line is better than yours. It could be worse.
Yeah.
I'm just going from my graph, you know?
Yeah.
Okay. Do you see this guy right here? The getting of the average apparent magnitude, this is the average apparent magnitude, was going to suck. And it was going to suck because you guys were going to have to take the average of all of these numbers. Now, it's 220 already, and I'm feeling kind of bad for y'all, so I'm just going to give you the answer. The average of all those numbers, you can verify for yourself if you want later, is 15.56. Let's plug that in here.
I trust you.
Yeah.
Yep.
But I'm gonna check it anyway.
Why?
Okay, so now we have to do the apparent average minus the absolute magnitude. What does that come out to be? Watch out with your negative subtractions. You have to punch it in like this.
19.06.
Minus 3.5, and then you put the negative in. 19.06 is correct.
Yeah, I was really lazy and knew how it worked out, so I just put plus.
Okay, cool. All right, we're almost done. Now, to go from it, this is what's called the distance modulus. The distance modulus is a weird way of measuring distance. It's the difference between the apparent minus the absolute magnitude. This is basically a distance measured in magnitudes. We can use the last page of the graph to convert 19.06 to a distance. If we go to the very last page,
Did
let me get organized here.
Yes. No, you actually did 12 yesterday.
Yeah, I know.
How'd you end up doing 12?
Could I just said I'll just finish the lesson?
Lesson's almost over.
Why do you look like a dopey skeleton?
That's what I am.
So there's 19. 19.2468. That's 19.2. So 19.06 will be like 19.1, right?
Yeah.
Pretty much.
Yeah, if you round it.
It'll be somewhere in between 19 and 19.2. We got to go up to the line here, so let's do this carefully.
Knew I'd find a use for them. Meter 6.
I'm up at about 65,000.
Yeah, hold on, wait, let's see. We have to be careful with this log graph. Mine's right in between these two. Oh yeah, you're right, Sal. It's, no. Look, if you go across, I think it's 6,000, 66,000, because this is 65,000 and mine seems to terminate right there. It's a really tough call. It's definitely between 60,000 and 70,000. Each of those are 1,000, each tick mark.
Yeah, maybe you're right. I do hit a little bit before 65,000. So I'm thinking
I hit a little after.
after.
My dead smack in the middle.
In the middle, it's 65.
Yeah,
Now-
why don't you just
Hold on, on the
average
other
it?
side. Hold on.
I think it's
How's
60,
that?
66,000 is what I'm getting.
I was at 18.9. Hold on.
My best guess
6.
is 66,000 parsecs.
About 66,000.
I'll accept 65, whatever. Oh my God, that's it. That was kind of brutal, I guess. Guys, I had never done this lab before. I'd never done this lab before in this context over the internet. So this lab's always a little tricky, but it's nice when I'm in person with you because I can kind of check everyone's work. But basically that wraps it up. We got the distance to the Large Magellanic Cloud. So what papers do you need? You obviously need this paper that we just did. Hold on. This paper that we just did, which has the period of the new variable star and all of that stuff, right? You need that. You also need to submit the back side of it, which is your period-luminosity relationship. Okay? And you also need to submit 15.3, which has this stuff here. So 3 pages. Actually, yeah, it's 2 pages, but one is front and back. You guys got that?
Can I see the graph, the curvy one?
Yes. Let me share my screen again.
For it.
Hold on, let me flip this. My phone is not frozen. Oh, here we go. Whoa. Well, we got major lag here. Hold on, whoever said that, just give me a second. Does that help?
Yeah, that's perfect.
I have a quick question. If my chart looks like this, like where you write in the numbers, do you want me to send a separate picture so that you can see it better?
Hold on. I need to see what. Let me stop my share here. There's a weird lag. Anyways.
Oh, I'm sorry. I didn't want to interrupt it.
That's okay, Ellis. Wait, let me go to speaker view and let me zoom in on you just for a sec, Ellis.
Okay, sorry. I didn't realize I wouldn't have.
Oh yeah, some of the charts. This is an older version of the book. That's kind of there. That's okay, but I think you're gonna have to draw your dots. Your plot. Let me. Can I draw on your screen? Let me see here.
Yeah, I like messed up early on, so I'm just gonna like look at your chart later, but like for the numbers.
Oh, what do you mean you messed up? Yeah,
Well, I had to like erase like half of them.
Oh, I'm sorry.
So I started over, but
there is a way for me to draw on your screen, and I'm trying to figure out how to do that so I can show you what's going to happen. How do I?
I'm sorry, John.
Okay, so I'm just going to kind of shoot. You can't see me pointing. On yours, the second camel. I remember this older version of the lab book. It kind of looks like a sawtooth with like 2 humps, 2 camel humps, right? The curve looks like.
Yes, yes.
Right? Do you understand what I mean now?
Yep.
The second camel hump is actually going to go right up through where it says log P. That's how it looks on that one. It's kind of weird. So your dots are actually going to be kind of fighting with your numbers. But it should look the same. You should get the same values is what I'm saying.
Okay, but the camera might not capture this as well. Do you want me to send it separately? Or I wrote the same thing you did. I just don't know if you'll be able to see it, like when I take like a long picture.
I think I will. You're going to take the picture with your phone?
Yeah.
I think it'll be okay.
Okay, just making sure. Sorry to interrupt again.
No, we're talking. This is a dialogue. It's more fun this way. Just plot your points, keep those numbers, make sure they come out approximately right. Like we got 4.8 days on ours, right? The only difference between yours and mine, and this could be true for other people who have an older version of the lab book, is the newer versions kind of, sorry, everything's backwards. The newer versions tucked the numbers up here, but on yours, the second hump actually goes through the numbers. But you should get the same values. You should end up with 4.8 days between your two camel peaks, okay?
Okay.
I don't know. Is there any way I can help you plot those points, or does anyone else need help with that? It can be a little confusing, but usually once you get the swing of it. My technique is to use a ruler and put a ruler at the Y coordinate and then go up with my finger from the bottom. I find that works for me the best.
Oh, okay. Is that the point that is like almost 2.5 and then 15.2 or 15.2 and then?
Hold on. Let me share screen.
Because I only like started the first hump, but I didn't get all the way through.
Okay, hold on. Let's see if I can, because you're not going to be the only one with these issues, Ellis. I know from experience doing this, that people can get a little messed up. And so that's my job, is to help with it. This Zoom is acting really irritating. It's. Okay, hold on. Let me try this again. Stop share. Share screen. Boop. 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 There's like this weird latency that I don't understand. Wait, I got a better idea. Since this is giving me trouble, I got a better idea. I've got a scanner right here below me, thankfully. And I think I can scan this pretty darn quick. Let's try this a different way. Where's HP scan? I had that open. Here we go. Okay. So let's save homework, astronomy homework scans. Astronomy 1020 lab Cepheid curve. Okay, let's see if we can look at that bad boy. Okay, cool. Can you guys see what's going on here?
Yeah.
So let's take the hand tool. The data point you were asking about, I think, let's get my annotate here. You were somewhere around here, like when it goes to 5.20, there's your 5.20 right there, right?
Mm-hmm.
And it goes to 15.84. Oh, shoot. Do I not have? Oh, okay. There we go. So 15.82 is here, and that's 15.84. Ooh, I can use my line tool. I should have done all this on the computer. So there's 15.84. Let's see if I got it right. There you go. And there's 5.2. Can you see that? So that's where you ought to be.
Yeah.
All right, and then that's just a reference, right? The next one is 5.38. But I said the hell with 5.38. I'm going to make it 5.4, which was here. So there was 5.4, and that was at the same height of 15.84. Do you see those two there?
Yeah.
That's where it starts to turn around. And then you
Okay.
kind of keep going like that. Remember, we're rounding the time to the nearest tenth, but we're not rounding the magnitude. And you also have to watch out because things go in the other direction. It's increasing downwards, which is confusing. Okay, cool. So Riker, hold on. Let's go to 90% or 85%. I'm just trying to see where I can get the best view here of everything. Okay, that's not good enough. Let's go to 75%. Riker, do you want to bang that? You want to snapshot that?
Yeah, I'll take a picture of that and put it in the Discord.
That
where
way
I put my phone.
to it. Thank you.
You can take screenshots too, Riker.
Actually, wait a minute. Riker, I got a better idea. Why
What's
don't
up?
I put it in the chat, right? Can't I do that?
Whoa.
Let's just blow some. Wait, how would I do this for the later students?
I don't know. It's giving me an issue with the chat. That's why I'm saying I'm not putting it. That's why I'm putting it in the Discord.
No, hold on. Watch this, Riker. I'm going to share a file, and I'm going to go to Black Terabyte Astronomy 1020 Lab Cepheid curve. Boom. Riker, will you take that file from the chat and put that in the Discord for students who are watching later?
Yeah.
Did everyone see that? Ellis, did you see that I shared my graph with you?
Give me 1 second. I should be able to get that in the Discord now.
Ellis, in the chat, I gave you the scan. Can you download that from the chat? I don't know exactly.
I only see FF. What page number? Thank you. Got it.
All right.
But Ellis,
PDF. The PDF is under the tab labeled Lab Discussion in the Discord.
Wait, Ellis, on my chat, I don't see underneath. I got it from Riker to everyone. There's something from me to everyone, which is a file.
Oh.
Does anyone else see that file besides me?
I see it.
Yeah.
Hope sees it. Morgan sees it. Okay.
It doesn't show what it is until they open it.
I don't see anything from you though. Like I don't have like your name out.
Do you see my hi?
Oh, now I see hi. Okay.
But no, wait. The file is above hi. Weird. Maybe you're. See, hold on. Let me see if there's like settings or something.
I'm sorry. I took a picture of the one that you had like before. I just can't.
Okay. Well, as long as you have something to base yours off of, so if you're worried that you're doing it wrong, that's all.
Yeah. Thank you so much. I appreciate it.
Okay.
I resent it just in case.
Thank you. Maybe you can't see my files. I don't know.
I don't know.
Okay.
I mean, everybody else can, so I think it's just me. But
well, I don't know. I'm thinking
All
about.
I see is the hi.
Oh, okay.
Same with you, Michael?
Yeah, that's all I see. I mean, I have it written down, but
There's
all I see is the
non-video
hi.
participants here. There's people watching later, so there's a lot of people who could be having that same issue. So it's worth talking about it. It's not just you. Okay, so I think this is the end of our lab then, correct?
Yep.
I hope.
We have one more lecture and one more homework.
That's sad.
It is very sad. We'll be doing chapter 18 homework this week, okay? And then you're all going to get all your papers into me by Friday, right?
Mm-hmm.
You guys I see each week, so I'm not worried about you, but it's the people that kind of come in and out of my life here that I'm concerned are going to start crying at the end of the semester, and then I'm going to have a very big box of tissues to manage these issues. Anyways, hopefully that won't be too many people. Any other things that we need to talk about or think about? You know where to submit this, right, Lab12?
No.
Questions?
Were you able to see all of the things that I sent you? Because I looked back on some of our past like homework assignments and labs, and I saw 6 assignments that didn't have anything, and 1 had a 0. So I mean, if you haven't looked at it yet, it's fine. Sure.
I'm sharing my screen with you now. I am really, really behind on the grading for this class, okay? Because I've just been a huge damn slacker. Let's go to my needs grading panel, and let's see if you're in there. There's going to be a lot of people in there. I have 150 items to grade. I've got some work to do. Oh, snap.
I feel the same way. So.
All right.
Yeah, I feel the same way. I think we all have a lot of work to do.
I promise you. So, Ellis, I see that you've submitted homework 10. That's good.
Okay.
And homework 7. So I am getting your things. I just haven't graded.
Okay. Yeah. One of my teachers told me that like half of the assignments that I was sending into her, like she couldn't see. So I had to like email all of my assignments to her again. So I just wanted to make sure like.
Wait, hold on. Let's click on your, this is, I can see your stuff. That looks great.
Okay. Just making sure. Yeah.
It looks okay.
just okay.
You guys want to grade it for me? Is that what you're saying? All right. So Ellis, it looks like everything's cool. It's just that I've been kind of a slacker, and I kept up with the 1010 stuff a little better, but the 1020 I'm behind on. Honestly, it was kind of frustrating because people were like, I was trying to grade like all of one. There's a reason why I was slacking. People were submitting like lab 10 in different chunks. So I would grade lab 10 and I'd think it was done, and then I would get like another batch of submissions. And it got so frustrating, I was just like, I'm just gonna wait until everyone submits all their lab 10s before I grade it.
Yeah.
Doing it in one chunk instead of like choppy piecemeal, you know?
Mm-hmm.
But this week I've got to clean that up, and maybe I should try to get that done before Thursday so everyone can kind of check and make sure they've got good grades, you know, because you want to make sure you don't have any zeros for your attempts, and I can understand that. You guys might also be wanting to calculate your final grade using my rubric, which you guys remember. You'll want to calculate your final grade so that you can make a decision yourselves about whether to ask for a letter grade or a withdraw pass. I'm assuming for the people I'm talking to here, the letter grade is going to be your better option, because with all your good homeworks and labs, your grades should be pretty high. They should be in the A, B.
Yeah, this is the only class that I got the letter grade for.
Oh, that's cool. That makes me feel good. That means that you're invested. Okay, so that's great. So I'll try to get that stuff done to give you guys enough time to make that decision. And you can of course ask me what my estimate of your grade is, and I'd be happy to share that with you.
Great.
Okay. Well, I'll stop the recording. I'll save the chat, and I'll see you guys on Thursday. Sound like a plan?
Wait, do you remember when you said mic drop last Thursday?
Yeah.
And then I threw myself out of my chair and I hurt
that was
myself.
pretty funny.
Is that recording?
Yeah, I had a bruise on my back for like 3 to 4 days, and it was big.
Maybe now we should just do pencil.
No. We don't need to do that again.
All right, yeah, no more mic drops.
No.
Maybe we should do a chicken drop. That's what we should do. All right.
Oh.
Be obliged.
Duck drop. All right.
That hurt me significantly less.
All right, I'm stopping the recording.